we can start now. Today we are happy to have David Shih. From Rutgers, he's on sabbatical on the Berkeley. He will talk about the new approach to anomaly detection.
Okay, well, thanks for having me here. It's a real pleasure to visit, as always. So today I want to tell you about something I'm pretty excited about, which is new ideas and new approaches for anomaly detection, primarily focused on LHC data. But if I have a chance, I'll mention a bit about what we're thinking about applying it beyond that. So let me just begin. Let me just begin by way of a little bit of motivation. I think so. At the LHC, we have the highest energy collider ever built, generating huge amounts of data. Let's not forget this. Okay, so there's 600 million collisions per second. There's 25 gigabytes per second of data that we're saving to take. That amounts to tens of petabytes per year that we're collecting. So there's this huge data set at the LHC, and although we haven't found any new physics yet, I think many of us believe that we haven't looked everywhere yet. So there's, I think, still enormous discovery potential for new physics in this data. Okay, so but yet a lot of people are perhaps getting discouraged because there have been thousands of searches for new physics at the LHC, and yet there's been nothing but limits and null results, right? So that does wear on you after a while. But then, so the question I want to raise in today's talk is, what if the new physics is hiding in the data, but we haven't looked in the right places yet? Okay, so you might be under the impression that, oh, we've looked everywhere already. So if we haven't seen it yet, that means it's not there. But I want to hopefully convince you today that that's not the case. Okay, so here's, for instance, a benchmark example that my collaborators and I released as a public data set as part of this LHC Olympics 2020 data challenge that we organized. So I'll tell you a lot more about this later in the talk. But here's an example of a new physics scenario. So a Z prime with some mass, some fairly large mass, that decays to two bosons, X and Y, that have different masses, 500 and 100 GeV, let's say. So these are much lighter than this, and so these come out with a high amount of boost. And then when they decay each to a pair of jets, their decay products are highly collimated into two large radius jets. Okay, so here's a scenario which there's no explicit search for this at the LHC, and if you go through all the searches that have been done, you can convince yourself that pretty much the only search that would be sensitive to this right now is the vanilla dijet resonance search. So the most basic dijet resonance search. And that would not be very sensitive to this scenario. And in fact, I'll show an example later where this could be sitting in the data, or in the near future data, let's say, with, say, 1 sigma significance in dijet resonance search. But if you were to look in the right place with, putting in all these different masses and the dijet resonance nature of this story, you could get it to be like 10 sigma. Okay, in the current data set.
Why isn't the dijet search sensitive to it? I can't.
Well, it is, just not sensitive enough. I mean, there's... It could be more sensitive, is what I'm saying. Yeah, it's not sensitive to it, but it could be way more sensitive.
You would see a bump, but you wouldn't necessarily...
You would see a bump in the dijet resonance. Well, you would see a bump at 3.5 TeV, but it would not be a big enough bump to be significant given the numbers I'm going to show you in a bit. Eventually it would be sensitive, but we could be discovering it now if we did the analysis the right way, is my point. Okay, so what I want to sell to you today is hopefully, there's a new paradigm for doing searches at the LHC, which I think we should invest more time and effort in, which is doing things more model independently. Okay, so can we search for new physics more model independently and fill the different gaps in our coverage, for instance, the previous benchmark model? Okay, and so what I'll be telling you more about today are there's been a number of interesting new ideas put forth recently for how we can do more model independent searches at the LHC using the latest, greatest techniques borrowed from machine learning, unsupervised machine learning. And so just very briefly, so one of the things I'll tell you about is an idea using something called neural density estimation that Ben Nachman and I proposed at the beginning of this year to look for overdensities in the data that could be coming from new physics. So one idea is you could take this bump hunt that would be somewhat sensitive to the scenario proposed before, and then in some additional features, for instance, end subjettiness, the mass of the two fat jets, there would be an additional overdensity in the data somewhere where the signal is localized. And if so, you could derive a way to get at this overdensity. You could cut on that and enhance the significance of the bump hunt. So I'll show you in more detail what you can do with this anode method on the LHCO R&D data set, where you can enhance the significance of this bump hunt by up to a factor of 7 on this example model. And in a way which you put a minimal assumption about what the signal model is. You're not telling it explicitly to look for this to look for this model, but it can find the overdensity anyway. Okay. And another idea that we had together with Anders, who's now working at Google, is to use background simulation, which we assume the background simulation is not good enough to compare directly to data, but it is good enough such that it's close to the data. And so we could try to reweight the background simulation to data and search for deviations from the background model. So we show that we can get good sensitivity, again on this benchmark data set, down to S over B in the percent level, which is could be enough to discover something like this now. Okay. So let me just now.
Sorry to
yeah,
go back.
of course. Yeah.
Maybe details don't matter too much here, but should we be shocked that the different Monte Carlos are so different?
Oh yeah. So I'm going to explain this plot later on. But what this is, yeah, there's a lot going on here. What this is we took data to be Pythia generated, and we took our simulation to be Herwig generated. And so the differences between the two are large enough. We make sure that the differences between the two are large enough that if you just train a classifier to distinguish data and simulation, so Pythia and Herwig, it wouldn't find the small amount of signal buried in the data. Yeah, so that's this blue curve here. So it still works to some extent, but not as well as if you reweight the simulation to look more like the data, and then repeat this procedure, you can get better sensitivity down to lower S over B. And then the red curve is if your simulation were perfect, if your simulation was Pythia also, the same Pythia that you used to generate the data, this is the best you could ever possibly do. Yeah. So I'll explain that plot more in the rest of the talk. Thanks. Okay, so here's an outline of the rest of the talk. I'm going to give you an overview of all the different new physics search strategies, or many of the new physics search strategies at the LHC, which you're probably familiar with a lot of this stuff, but I'm going to remind you about that. And then I'm going to talk about new ideas, in particular for enhancing the bump hunt. Okay? And finally, I'll tell you what's going on with the LHC Olympics 2020 thing that we organized. Okay, feel free to stop me with questions anytime. Okay, so let's just give a brief overview of new physics searches at the LHC. So I think generally the idea in searching for new physics or any kind of anomaly in the data, in any kind of data, is to find some kind of discriminant that's sensitive to your signal relative to the background, right? So I'm not saying anything very interesting, but so the idea is always to find some function of the data where the signal, ideally, it populates a tail or something, and the background doesn't, so that if you cut on this discriminant, you purify signal to noise. Okay. So now what discriminant are we generally supposed to use? What should guide us in finding this discriminant? Obviously, so it's like tennis, you should always hit the ball to where your opponent is not, right? So we should look for places where there's signal and not background. But formally, what we're doing when we do that is something called the Neyman-Pearson lemma, which is a very nice result in statistics that gets used a lot, which says that the most powerful, and powerful has a technical definition, which I won't get into, but the most powerful or optimal discriminant between two simple hypotheses, called them H1 and H2, is given by the likelihood ratio. Right? So if hypothesis H1 has a probability density given by L of x, condition on H1, and hypothesis H2 has this probability density, then the best you could ever do to distinguish the two hypotheses is to construct the likelihood ratio. Okay? So that's called the Neyman-Pearson law. And so we use this all the time, maybe without realizing it. So two examples which I'll focus on in today is one in which H1 is some specific signal, like supersymmetry with a gluino at 2 TeV and a neutralino at a TeV or something. So some specific signal, H1, and H2 is the standard model background. Okay, and so this is the conventional model-specific search strategy. Okay, and the other example that I'll focus on is when H1 is the data, okay, the data itself, and H2 is the standard model background. In that case, this is what you would want to use for a model-independent search strategy, something more along the lines of unsupervised, open-ended anomaly detection. Okay, so I'll have more to say on this in a moment, but just want to make sure that that's the two cases we're going to consider today. Okay. So let's talk about the most common approach, which is model-specific searches. Okay. So in that case, you have a specific signal in mind. So I should have been more specific here, not just all of supersymmetry, but supersymmetry with a particular spectrum and decay branching ratios and masses and everything. Cross-section, fully specified. So a specific signal model in mind. And then what do? We take this signal model, we simulate it, right, using MagGraph and Pythia, and then put it through Geon4 for the experimentalists, right? So we simulate the signal, and typically we might also simulate some of the main backgrounds, okay? And then we would use these simulations to construct, basically to design a set of cuts on a set of relevant features, like MET, HT, etc. And then we optimize these cuts to have the best sensitivity, best discovery potential, or to set the strongest limit on the signal model. Okay, and so that's what we're doing when we look at this likelihood ratio between signal and background. Okay, so I would call this method both signal and background model dependent. When we're constructing a discriminant, we're relying heavily on simulation for the background model. That's background model dependence, and we have a very specific signal in mind, so that's signal model dependent.
So how do you know if X is complete or has all of the features? Right, because your likelihood is no better than how far you characterize the events. Right?
Indeed. So I think you're asking, what's the choice of X we should be using, right? And yeah, so the Neyman-Pearson lemma, I think, is conditioned on if you have this set of features, or if your data is described by this space of X, then this is the best you could do. You can always...
But it doesn't tell you which set.
It doesn't tell you which set of X you should be using, indeed. Yeah. So that's another sort of bias that we're putting into the problem, right? And so, if you're looking for supersymmetry, you might want to use MET. And if you're not, you might want to use something else. So, yeah. I don't know if that's...
in the example you gave, disentangling the subjects somehow.
Right. Yeah. So that's one of the biases I'm going to put into the density estimation story. Is we're going to only use just the right features for that. But yeah. Okay. So I think I don't know if people are aware, but I think the vast majority. It's a weird situation, I think, but the vast majority of searches at the LHC are of this type. Optimized very specifically on specific models. Okay, and I already said it, but we haven't seen anything using this approach. So maybe it's time to try something different. Okay, so what else could we do? Currently, the collaborations both have something model independent that they do, under different names, like the general search. Okay. This is a CMS institution, right? Yeah. So on CMS it's called music, I think. And on Atlas it's called the general search. But and there's a long history of doing it this way. and it's all the same. It's all the same approach, I think.
Did Atlas publish their general search?
I have a slide showing you the publication history. I think not. Yeah.
Yeah.
So, yeah, CMS actually managed to publish it, which was maybe you shouldn't have. Yeah. Okay. So the idea.
Publish more.
Huh?
We could publish more.
You have a looser publication committee? Or?
I mean, with more data.
Ah, yeah. So, okay, so the idea, correct me if I'm wrong, the idea is, in all these approaches, is to compare the data itself to simulated standard model background in as many one-dimensional histograms as you can think of, basically. So you look at every possible kinematic feature you can think of, like PT, HT, PT of the third jet, you know, delta R between jet 2 and jet 3, etc. So you think of every possible kinematic feature you can, and you make 1D histograms out of all of them, and you compare data against background simulation. Okay? And of course, your simulation should include all the processes of the standard model with the right cross-sections and right differential cross-sections, etc., in order for this to work, right? And also, so that's what's actually done in the general searches. And recently, theorists have been proposing basically the turbocharged version of this, which would be to train a DNN, a deep neural network or something, on the full phase space of the data. So not binning it and not doing one-dimensional histograms, but say taking all the 4 vectors as inputs, or making a big list of all the high-level features you could think of, and feeding them all to a DNN in order to construct this likelihood ratio. But again, training it as a classifier against data versus background Monte Carlo. So that's sort of the best you could do, the most sensitive you could do with this kind of approach. But currently, that's just a proposal from theorists, as far as I know. Okay, so this general search idea is signal model independent, I would say, because it doesn't assume anything about any signals. It literally just takes all the data to make the numerator, right? But it's background model dependent because it's simulation based for the backgrounds. Okay, so it assumes we understand the standard model well enough to make this comparison. Okay, and actually, what I learned looking into this, preparing this kind of talk, is that there's been a long and I would say neglected history of searches of this type. So not a lot of people know, I think, but we've been doing this since at least since D0, and a lot of it goes back to this guy, Bruce. And I think his DNA runs through all of this somehow, right? Many former collaborators, students, postdocs of his are carrying the torch. And so the current versions, so it goes back to D0, there was one on Hera, and then Bruce went on to CDF and repeated it there. And now CMS and Atlas each have their own versions of this. Okay? And I think, yeah, the Atlas, wait, no, the Atlas one was published.
Oh, okay.
The CMS one is not published.
So you have to take back the negative
I think
implication
Yeah.
you made earlier.
Yeah.
I think there is a paper.
Oh, now there's, okay, I last checked this a couple months ago.
Yeah, me too.
Before we go on, can you go back 2 slides? This one.
Mhm.
So I guess why I'm getting a little stuck here is that, you know, typically we try to measure all of our most important backgrounds in the data.
Yeah, so
Is that-
in other versions of this talk, I'm more careful, but yeah, so this is just about the discriminant. So how you optimize the cuts.
right.
So I'm not an expert on how you do the analyses, but my impression is a lot of the cut optimization is simulation based. Now, when you actually estimate the backgrounds, it's sort of a factorized thing, and there you're of course not being so naive. You're using the data-driven backgrounds. So, but when you're designing the next iteration of JETS plus MET, I think you're just using simulations for the most part.
I don't know, I'm thinking about our cases where, you know, the tau fakes are the largest background, and so we're measuring all of that in the data.
Absolutely, yeah. So that's for the background
That's the
estimation.
background estimation, but you're right, that for the signal optimization, it's still sort of a hybrid.
Mhm.
Okay.
Okay.
It looks like you're right, that it's just a certain note.
This is just a pass, right? Yeah. Yeah. I don't know.
2014.
Yeah, it's from, right. It's
So
old.
that's when they started. That doesn't mean that's-
Oh, that's when they started. Okay, yeah. I thought it just came out recently. Yeah. Okay. But yeah, so over the course of 20 years, I think this approach has, the essence of it has not really changed. It's 1D histograms and background simulation versus data. Okay, and so how well does this sort of thing work? Well, this is what I think of it. This is an example. Admittedly, this is not totally fair. This is what Bruce found on CDF, and you might argue that the simulations are better now, but there's also more data. So I'm not sure that things are that much better. And so this was one of the most discrepant histograms in the CDF version of the general search, showing you the what is this, delta R between Jet 2 and Jet 3 in the, it doesn't say, I think it's in the BBJJ final state. And you could just see that the two don't agree at all between data, which is the black dots, and the simulation. And of course, they didn't think this was new physics. This is a huge discrepancy, many sigma significant, but they said, it's probably the parton shower. Okay. So what this approach generally can find are places where the Monte Carlo simulation doesn't agree with the data. And it's not at all clear to most people, I think, that this will ever converge. There aren't enough theorists to work on simulation, tuning the simulation, or next to next, leading order, corrections, etc., for the simulation to ever be so good that we could compare it directly against the data.
But if we do it this way, we'll end up tuning out all new physics.
Yeah, also, well, if it's a matter of tuning, then yeah, right. And if it's a matter of, if it's a next to leading order calculation from first principles, then maybe, yeah. But right, if there's just some knob in Pythia you can dial and fit them all, then...
Steve Rana did just that afterwards, so he got one.
Right, that's kind of scary. Okay, so yeah, so that's currently mainly the only alternative to the model-specific searches. Okay, and then there is one other model-independent approach that has a long history that we shouldn't forget, which is the bump count, right? And so here we're taking one single feature, like invariant mass, and we're constructing the likelihood ratio basically between data and the background. But now the background is derived from the data, right? And it's using the sideband method for the bump count, right? So we assume, here we sacrifice a little bit of signal model independence. We assume that the signal is localized in M. We also sacrifice a little bit of background model independence. We assume the background is smooth, right? But what we get in return is we get this nice way of looking for new physics, mostly model independently, where we can use the sidebands to interpolate the smooth background into the signal region and get a data-driven estimate for this, the denominator of this likelihood ratio, right? So this is a classic method. We know that. And it's been used in many discoveries, right? We've discovered the Higgs that way. We discovered the Z that way. Although, I don't know if it's true or not, but a lot of these events were actually fake in the end. Or, no? Yeah. This is the Rubia discovery, yes. Right? So most of them were later shown to be background or something? Or I don't know if that's true.
I don't remember that.
Okay. So, but anyway, it's a classic method that we believe works. We know works. And it's also a classic search for new physics. It's almost always the first search that's made public, that's published by the collaborations every time there's a new round of data. Okay, it's relatively easy to run, I guess. And also it casts a wide net for new physics, right? So any hypothetical BSM particle that decays to a pair of jets could be seen in this way, right? Okay. And many hypothetical things that don't exist couldn't be seen this way too, like the 750 GeV diphotons. Okay, so good. So that's my overview of how we search for new physics at the LHC, cast in light of this likelihood ratio, the Neyman Pearson lemma, and so we've talked about how most searches live down here in terms of signal model independence and background model independence. That's where we mostly live. There are these few attempts to do things more model independently here, which are heavily background model dependent, but signal model independent. And then there's the classic bump hunt, which lives up here, which is mostly background model independent and mostly signal model independent, but not as much as this one is. I didn't talk about this, but there are a few searches out there that have a very specific signal in mind, like there's some TTH or something with H to gamma gamma. that, so it's not really a search for new physics, more of a standard model search, but they have a particular signal model in mind, they simulate, but then they train a classifier between that simulated signal, and the data in control regions. Like they invert some lepton selection or photon selection, and so they train signal versus data to derive this likelihood ratio.
That can also work even if there's signal contamination in the data, right?
That could work if your TTH or whatever is bigger than expected. Exactly, yeah. So you could, or it's not TTH but has the same final state. So, it could end up catching something else.
Even if you tell the neural net it's a supervised learning, even if you tell the neural net all the data are background, even if some of them are signal, it'll still learn to pick out the signal.
If you tell it all the data are background, even including the signal.
Yeah.
Yeah.
It still works.
If you train the data against the signal, you mean?
Right.
Yeah.
I haven't seen anyone actually do it, but it is technically possible.
Yeah, I think in the one,
Correctly,
It's
still, as long as you interpret
the
it.
neural net still minimizes its error
Yeah.
by calling the signal and the data.
yeah, it'll pay that little price of getting the data wrong because the signal is 50% of your training sample. Yeah, sure. Yeah, I think but the ones that have the one I know that did this, the actual analysis, I think, didn't try to minimize the signal contamination.
You have to have a model for what you're looking for.
Okay, so that's the three that we've talked about, and then there's just a few analyses that try to do that. But then what I want to spend the rest of the talk talking about are a number of new ideas for model agnostic searches proposed recently that live up here. Okay, that I think, so these are all proposals for the way how you could analyze the data to find new physics that made by theorists or maybe some experimentalists too, writing PhD papers. But to implement them in the data would be really cool. Okay. So so these are all the new approaches on one slide. Okay, and so what I'll briefly mention in the rest of the talk is autoencoders, but I think many of you have heard me talk about that before, so I'll just say very briefly what that is, mainly to set the stage for two new ideas that I've worked on, anode and salad, and I'll also describe this koala method because it sort of has something to interplay between with the other methods. Okay. All right. So good. So let me briefly talk about autoencoders. So this is already a bit of an old idea from 2018, and so it's an idea that Marco Frina, Yushiro Nakai, and I proposed, and simultaneously the Heidelberg group, so Tillman Plain and Gregor Kaziska, Jenny Thompson, and collaborators. So we both have the same idea, which is that first of all, the background is that in the real world, say not our fantasy world, in the real world of credit card fraud and terrorists and things, people use autoencoders to look for anomalies in the data, and so you just Google anomaly detection and you find autoencoders. So a natural thing to try was to try this on LHC data, where here our anomalies are new physics. You could also imagine using this for anomaly detection of, say, detector quality problems, which I think is also a potential application. But yeah, so we both said, what if we try to apply this autoencoder anomaly detection idea to look for new physics? And what the idea is so what the autoencoder does, it's a machine learning algorithm, like a deep neural network, for instance, that you train to map a set of inputs back to themselves. Okay, but you do it in such. I mean, this would not be interesting. It would just be the identity mapping, right? Were it not for the fact that there's some information loss. So the autoencoder has a compression down to a latent space that's a much smaller dimension, and the compression forces the autoencoder to only keep sort of the most relevant amount of information necessary to describe the data set. Okay. So you can also use the autoencoder for compression algorithms or dimensionality reduction. Okay. So, but to use it for anomaly detection, what you do is you consider the reconstruction error between input and output. So you say take the difference of the two squared and sum the mean squared error between the two. And then you cut on that reconstruction error and use it as an anomaly threshold. And the hope is that if the autoencoder sees the background a lot more than the signal, let's say the signal is very rare, then the autoencoder will learn to, it only has sort of finite capacity, so it'll learn to reconstruct the backgrounds very well, but then it won't be able to spend its finite capacity to also reconstruct the signal well. So if it's working, the backgrounds, I don't know if you can see this gray thing, it's more clear on my laptop, but this gray thing here is what the background reconstruction error would be. And then these colored histograms are what various signals could be. So we tried this out. We took the background to be QCD jets in some PT range. We took two different signals. We wanted to see if the autoencoder could discover tops. So we took highly boosted tops that decay hadronically. So they make a fat jet cone. Okay? And then we also looked at 400 GeV RPV decaying gluinos, so also a three-jet topology. In both cases, they're highly boosted, so their decay products are large radius jets. Okay, and so we trained this on backgrounds plus also, so we did two different things. We trained it on just backgrounds. We also trained it on backgrounds plus a little bit of signal. And in both cases, we saw that it behaves as expected. The autoencoder would learn to reconstruct QCD very well, have a very low reconstruction error. And then when it sees the signal, it doesn't know what to do, and it produces on average, a large reconstruction error. Okay, so yeah. So it's important that it works even when there's a little bit of signal contaminating the data. That means you could hope to run it in a fully unsupervised mode, where you could hope to just train the autoencoder on the data itself, and it could pick out the signals. So that would be the hope. Okay. Now, just having a good discriminant is not enough to discover new physics, right? We also have to be able to estimate the backgrounds. And so we also considered how we would do background estimation and how we would turn this into an actual new physics search. And both of us independently realized, one nice way to do this would be to combine the autoencoder with a bump hunt in the jet mass, right? So, and then you can estimate the backgrounds using the sidebands in the mass. And then both of us realized that, that there's a fundamental limitation to this approach, which is that this only works if cutting on the reconstruction error doesn't sculpt the mass distribution of the background, right? So if the autoencoder learns mass somehow, or is biased against mass, then when you start cutting on the autoencoder reconstruction error, you could sculpt a feature into your backgrounds like that. Then when you do the sideband method, well, basically the background doesn't satisfy the assumptions of the bump hunt anymore. It's not smooth, it has a feature in the signal region, and then you grossly underestimate your backgrounds in the signal region, and you would claim a discovery when in fact it's just background. Okay, so that's the problem. That's what you need to ensure for the autoencoder bump hunt to work. We found empirically that the jet mass distribution is fairly stable against the cuts if you do a CNN using jet images, and you don't look below 250 GeV. So we just found that empirically. And then the Heidelberg group did something more principled. They applied a decorrelation technique between the mass and the autoencoder reconstruction error to explicitly force the autoencoder to not learn the mass. Okay. So, but yeah, so you can try these different approaches on the data. Okay. But so what I wanted to say about the autoencoder mostly is, yeah, this is a nice, I think, a potentially interesting thing to try on the data. But also, it's uncontrolled, right? So what the autoencoder finds is uncontrolled, and it's not giving you this Neyman-Pearson likelihood ratio in any, I don't think it's learning to do that. Okay? So there's no guarantee of optimality, even in the limit of infinite training data, etc. What you find is what you find, and it's just sort of a matter of luck, maybe. And also, we saw that one way to turn the autoencoder into an actual new physics search is to combine it with a bump hunt. Okay, so that had us thinking, can we get more if we build in the bump hunt assumption? If we're going to do a bump hunt, can we get more if we build maybe a guarantee of optimality if we build in the bump hunt assumption from the outset? Okay, so that's what I want to talk about next. Okay, is enhancing the bump hunt. Okay, so now we're sacrificing the full model independence of something like the autoencoder. We're making an assumption about the signal, but in return for that, we're going to get a way to estimate the backgrounds and a guarantee of asymptotic optimality. Okay. So I think there's a growing number of methods that aim to enhance the bump hunt using additional features. Okay, so the idea is that if the signal is localized not just in some resonant feature like invariant mass, but also maybe it's localized in other additional features. So maybe there's some additional feature space where the signal lives here and the background is more diffuse. If you could figure out where the signal is localized and cut on that, you could grow the significance of the bump hunt. Okay. Oops. So let me just remind you again about the R&D benchmark model. So in this case, the primary resonant feature would be the Z prime mass, right? And there's a bump there, but it doesn't have to be very significant. And so here's a set of numbers chosen to be representative of, I think it was chosen to be representative of 50 inverse femtobarns, or maybe 100 inverse femtobarns. Anyway, something around now or the near future, so there's 500,000 background events, which are QCD digets, with some trigger on the PT. Okay, and then we put in 500 signals, just for the sake of argument. So if you look in a window around where the signal lives, so around 3.5 TeV, S over root B is 1.5, and S over B is 6 times 10 to minus 3. Okay, so if you just did the dijet invariant mass bump hunt with this data set and this level of signal, you would find 1.5 signal significance, ideally, not including statistical significance. Okay. So, but can you enhance that with looking in the additional feature space? So for this benchmark model, probably the best you could do, almost the best you could do, is to look at the invariant mass of the two fat jets. There's two fat jets in every event. So look at the invariant mass of the two and look at the n subjettiness, tau 2 ones of the two. So of course, saying that this is what I'm interested in is a huge bias I'm putting into the problem, but these are baby steps. Okay. So ideally, you wouldn't just have this short list. You would have like 20 of these. So, but the methods could find the anomaly no matter what, which 4 of them were lighting up or something. So, but let's just take these 4 for the sake of argument. So the signal is again localized in these 4 at a place different than the background, or the background, yeah, at a place different than the background. Okay, so if you could find the overdensity or find where the signal peaks in this additional feature space, you could enhance the significance of the bump. Okay, so the goal, again, is to derive a discriminant sensitive to new physics in the auxiliary feature space. And again, the optimal discriminant would be the likelihood ratio, now as a function of this auxiliary feature space X. In the numerator, the hypothesis is the data, and in the denominator, it's the background. Okay? And ideally, we would want to get the background estimate directly from the data. Okay? And so, indeed, what we're going to see is that using deep learning and using the sideband method, we can actually learn something that approximates or approaches this multidimensional likelihood ratio directly from the data. Okay, so we don't have to confine ourselves to just 1D histograms. We don't have to bin anymore. We could try to tackle a high dimensional phase space directly using deep learning. Okay. Right, and so then if you could cut on this discriminant, you could start from the bump hunt, in the original MJJ invariant mass variable. As you cut harder, you could grow the significance of the bump by quite a lot.
Each of these lines you're cutting harder on what?
On this auxiliary, discriminant on the auxiliary, yeah, right. Yeah. And this is taken from the Koala paper by Ben, Jack Collins, and Kyle Howe. Okay, So here's now 3 new ideas for enhancing the bump hunt. Okay, if I have time, I can get through all of them. So the first is by these characters, and they call it koala hunting, or hunting with koalas, not hunting the koalas. And koala here stands for classification without labels. Okay, so what's the idea? So it's a very nice idea. So we assume that the auxiliary features X and M are completely independent in the background. So let me explain what that means in more detail. But this is a strong assumption that they make about the nature of the data, or the nature of the features. But with that assumption, they can do a lot. Okay. So the idea is now you have the data in the sidebands, okay, and you have the data in the signal region. And in the so you assume there's no background. You assume there's no signal in the sidebands, but there could be the signal in the signal region. Okay. And so you train a classifier to distinguish these two. So it's all data, right? But you feed this data and this data to a deep neural network that tries to classify the difference between the two. And if these auxiliary features are the same in the signal region and in the sideband, then the only thing that the classifier, other than statistical fluctuations, the only thing that the classifier can learn is that here there's signal. Okay? On the other hand, if X and M are not independent in the background, if these blue circles are distributed very differently than these blue circles, the classifier will get distracted by that. It will learn the difference between signal region and sideband in the background, and it won't be sensitive to that signal. Okay, so that's why this assumption is required. So this is what's happening in equations. So if the classifier is near optimal, so if we've trained our deep neural network properly and it's big enough, etc., and it hasn't overfit, then it will approach the likelihood ratio by the Neyman-Pearson lemma, right? So this is also known as the likelihood ratio trick, and it's used over and over again in deep learning. So it's sort of like a lot of the best ideas in deep learning are relying on this likelihood ratio trick, including this thing called generative adversarial networks. That they're just using this. So anytime you train a classifier and it's near optimal, it's going to produce something which is from which you can extract the likelihood ratio. Okay. Anyway, so the koala classifier will learn this likelihood ratio. So it's the probability density for M in the sideband, conditioned on M in the sideband, in the data, over the probability density conditioned on M in the, probability density of M conditioned on the signal region over conditioned on the sideband. Okay. And by assumption, there's no signal here, so that's just data over background, but still we're living in the signal region here and in the sideband here, right? But again, by assumption, the probability density doesn't care about, in X, doesn't care about M, right? They're independent. So then this becomes this ratio, which is the one we wanted, right? So this is the optimal classifier for data versus background. Okay, and so that's how you can, that's why it's called classification without labels. We didn't put in any labeled data signal versus background. We just put sideband versus signal region. So those are the labels, if you like. And yet we get a classifier that's sensitive to signal versus background. Okay. So here's one slide about koala versus autoencoder. This is a project being done by Pablo, a student from Madrid. So here we're looking at comparing koalas versus autoencoders, sort of a direct comparison on the R&D data set. And the interesting trade-off between the two is that because koala is learning data versus background, it's going to only be sensitive to signal for relatively high S over Bs. Okay? So as S over B decreases, there's too much background, and it'll be sort of swamped by the statistical fluctuations in the background, and won't be able to pick up on this signal over density there. Okay. Meanwhile, the autoencoder can be run even when there's no signal at all. It works in finding anomalies even if it's background only, right? So the autoencoder is not going to be very sensitive, but it's not going to peter out as S over B decreases. So there's this nice crossover plot between the performance of the autoencoder, this is now plotting, if I treated these things as supervised classifiers and computed their ROC curves and then looked at their AUC, this is a measure of how sensitive they are to a signal. Okay,
Remind me
so
what AUC is?
the area under the curve.
Oh,
So yeah, so higher area under the curve is better, more sensitive to signal, better at discriminating signal versus background. So the autoencoder is basically flat. It starts to peter out as there's too much signal, like 10% or more. But up to 10% is basically flat, whereas the koala method is really good up until some threshold in S over B, at which point it peters out. Okay. So that's a nice complementarity between the two methods.
So what's the systematic uncertainty assumed this plot?
Systematic uncertainty. Oh, we don't have any systematic uncertainty.
Okay.
But, sorry, so, no, we're just training it on the data, let's say. So, in some sense, like, there's no theory systematics that we have to worry about.
But the background, there's no...
It's just the data. So, yeah, I mean, an extreme point of view would be that there's no systematic uncertainties.
But what about background? The background should be have some...
Yeah, maybe there's measurement uncertainties on the background, like jet energy scale or something. So when I quote this metric, this is, you could think of this as a purely, it's not even statistical because it's just the raw performance of the classifier. So it hasn't been smeared out or corrected for any kind of systematic or...
Okay.
And it's supposed to be in the limit of infinite statistics, right? So yeah, there's not necessarily any, well, no, actually this is all data driven. So some of the scatter you see is due to statistical uncertainty.
Okay.
Yeah. Okay. Yeah. We can't be in infinite statistics because we're doing this on the data. Yeah. Good. So yeah, every time you train the classifier, you may get a different result.
but that's not a systematic error.
I don't know. How do you?
I don't
how do
view
you?
it that way.
Yeah. Well,
It does, the classifier does what it does. The only way it would be a systematic error is if it behaved,
systematically.
systematically
Yeah.
differently from reality. But since you're training data against data,
Yeah, that's why I said, yeah, I've heard people take the point of view that there are no systematic
I
uncertainties.
think that's right. but
You're just
it's not.
doing, I mean, if you're doing a sideband fit on the data, there could be systematic uncertainties on the fit parameters, right? Or I don't know how you count those as statistical or systematic. Yeah. So in the background, this is not, there's no background estimation yet anywhere here. So if you were to estimate backgrounds, maybe from the data even,
Okay.
there would be some kind of uncertainty on that, I presume. How you classify that uncertainty on it. I don't know.
It ends up just being statistical, but that's an interesting philosophical.
Yeah, maybe it's, semantic. I don't know. Anyway,
Okay.
yeah. Asking a theorist about systematic uncertainty is probably not very, I don't know.
Okay. No, right.
I've never had to struggle with those.
Yeah.
Okay. Anyway, so that's the koala method. It's a very nice idea. It assumes, though, that X and M are independent in the background. Okay. So now, something I got very interested in, and Ben and I worked on a lot and put out earlier this year, is a totally different idea. Okay. So I should have also stressed. Sorry, I should have also stressed that one nice thing about the likelihood ratio trick and about this method, the koala method, is that you would call this thing, it's an important buzzword, okay? You would call this thing likelihood-free inference, okay? Just in case you never heard what that actually is. My understanding is at least one kind of likelihood-free inference is when you don't go after the likelihoods themselves, but just their ratio, okay? So in this method, you never know separately the numerator and the denominator, you just get the ratio, okay? Because you train this classifier. Okay, so this counts as likelihood-free inference. So what I'm going to tell you next is this anode method, which is not likelihood-free inference, but has different pros and cons compared to the koala method. Okay, so here the idea was that there have been recent breakthroughs in estimating density estimation, high-dimensional density estimation, using neural networks, and that could make it possible to directly learn these conditional probability densities that make up the numerator and the denominator, this likelihood ratio, directly from the data. Okay? So people have tried to do this actually, going back. Kyle Kramer told us that his thesis advisors at Rice tried this, proposed this for CDF 20 or 30 years ago. But there it was on the simulations, and it was using some k-nearest neighbors methods. Okay, so in fact, using neural networks, people have made a lot of strides in accurately estimating the probability densities of high-dimensional data. And so if you could apply this to this auxiliary feature space, you could, first of all, learn the probability density of the sideband region, right? And then you could also learn the probability density of the signal region, okay?
And then your aim is to do this in higher dimensions for x than 2.
Yes, we're going to do it for 4.
4.
And the dream would be to do it for, 8 or 100 or
Large numbers.
5,000 or, yeah.
Then the space is very sparse.
Yeah. So I don't know. I have not gone to the edge of what's possible, I think, but I'll show you. It certainly works for 4. Okay. Good. So this would be the dream, is whatever dimension you want, you could estimate the density using some fancy neural network. And then, because you've estimated this as a conditional density, as a function of x and m, the neural network is very good at interpolating. Okay, so as long as your sideband brackets the signal region, you learn this function, or the neural network learns this function, and then you could query it for values that it wasn't trained on. As long as it's an interpolation, it's actually surprisingly robust. Okay, so you get this automatic interpolation for free, and you get the probability density in the signal region of the background. Okay, so basically you can learn the distribution of these blue circles here, and then interpolate it into here. And the blue circles distribution could even depend on m, but because you've learned this entire function, you're robust against correlations now between x and m. Okay, so now you can get the numerator and the denominator separately and explicitly construct this likelihood ratio. Okay, so yeah, so we use this thing called a conditional masked autoregressive flow that was developed in 2017, but in principle there have been even more powerful things developed since then. It would be interesting to try those out as well. Okay. So this is what we found on the LHCO R&D data set. Okay, you can't really see the colors, but this is supposed to be red, and it's supposed to be the signal. And the background lives here. What we're plotting here is the likelihood ratio in the signal region, constructed using this anode method, versus the log of the background probability density estimate. Okay, so here there's high density, and here the data where there's high density and the data is not sparse, the probability density is very accurate, very tight. Okay, the scatter here is very small, around 1. Oh yeah, so if there was no signal and this method worked perfectly, you would get a ratio of 1, right? Okay, so indeed here there's no signal, and the density estimation is working very well. You get something tightly focused around 1, and it gets more spread out as you go to lower probability densities. But this is also where the signal lives at a huge overdensity. Okay, so this R is very large, 5 times larger than, the ratio is like 5 up here. So this represents a huge overdensity that's resulting from the signal. Okay, so we get a very sensitive discriminant that can see this, the particular 500 GeV, 100 GeV, etc. That we injected into the data, fake data.
We do use a model for the signal.
Well, here we biased ourselves by choosing the 4 features that work perfectly for the signal.
Okay.
So the dream again would be, can you do this without as much bias, like include, say, n sub j is 3.2 and 4.3, and more features like PT, so have a bigger list, and yet it could still see the signal for any other.
This came out last month?
This came out, what month are we in? Yeah, February. This came out in January. Yeah. Okay. Yes. So if you missed that, you missed my 2 other papers on that day as well.
Awesome.
So yeah. So here's
cross-list to experiment, right? FX.
Yeah.
Okay.
One of them we cross-listed to physics, data, and then the archive moderators tried to force us to put it out there, and then that delayed its publication by a couple days. We didn't want to have it be primary physics data, which I've never heard of before. Anyway, the moderators are kind of out of control. Oh wait,
I'm
you're
one of them.
you're one of them.
I moderate FX.
Yeah.
Which is usually pretty straightforward.
It's
Either it is or it is not.
So
Where's
we
the
emailed
factor of 7?
we emailed Chava and he helped us. Okay. So so anyway, so this anode here is this curve here. Okay. And so
It was I who pointed you to shallow, wasn't it? Okay, never mind.
Gregor emailed you. Yeah.
Yeah.
Okay, so this is the factor of 7 right here. The significance. This is now plotting the significance improvement. If you cut on this anode classifier, how much you can improve S over root B relative to not doing anything at all. And so that's this 7 here. Okay, so you can enhance the significance of the bump hunt by up to a factor of 7, which if we started from 1.5 sigma would be something like 10 sigma. Okay. And actually you can see we plotted here, this is the theoretical best you could do. It's a supervised classifier. And so that's totally unfair. So that would be the model-specific approach if you knew the masses exactly that you were looking for, 500 GeV and 180, 3.5 TeV, etc. So that's the best you could do. So the fact that we're living here and we can still get to 10 sigma is very nice. We put in something about the model, but not everything about it. And this is just a proof of some concept that you hope could get improved in the future. And by comparison, we also overlaid the koala method here. And you can see that the koala method does even better. And that shows the power of the likelihood-free method, because koala method doesn't try to construct the numerator and denominator likelihood ratio separately. Right? It just gets the likelihood ratio itself. And a binary classifier is always easier to train than some unsupervised density estimator, high dimensions, yada yada. And it just so happens that for this feature set, the 2 masses and 2 n-subjectivenesses, the koala independence assumptions are satisfied, mostly. So the feature space is a good one for the koala method. Okay. Another aspect of anode that was interesting is that, in principle, if the density estimation is good enough, you could try to estimate the background directly using the background probability density, right? You could just integrate that thing, in principle, to get the background estimate. And so this here is a ratio plot of the predicted background using this method, that's in orange here, versus the actual background. And you can see that it's within 10%, even within 5%, up until maybe this point, which is like a factor of 10 to the 3 reduction in the background. Okay, so it's fairly stable too. So if you trusted in this approach, you could get a background estimate that's relatively robust or calibrated directly from the density estimate. So you wouldn't even need to do a sideband method or anything. Okay. Finally, we considered what happens if you introduce correlations between the features and MJJ. In that case, the koala method should totally break, which it does. So the koala method is no better than random after that, whereas the anode method still has sensitivity, slightly reduced, but still pretty sensitive to the signal. So we introduced correlations in an artificial way, just for proof of concept. We said, what happens if instead of using MJ1 and MJ2, we use a variable that's linearly correlated with MJJ? But we introduced a linear correlation. I think we chose 0.1 here, so 10% correlation, just to see what would happen. So yeah, so that's where the anode method outperforms koala. Okay, I think I'm basically running out of time, so I'm going to skip the other thing that we did, which is using simulations. Bootstrapping from simulations to also search for new physics. And I just want to tell you briefly about the LHC Olympics in the last, say, 3 minutes. Okay?
5 minutes is okay.
5 minutes? Okay. Yeah, so I flashed the slides and it's recorded, so you can like slow-mo to see the slides that I just flashed if you want to see more about.
You will be uploading the slides to our.
I will be uploading
Yes.
the slides. Okay. So anyway, so let me just tell you briefly about this fun thing that we organized. So we wanted to facilitate a meaningful comparison between different anomaly detection approaches, and also, even more so, we wanted to spur the development of new ideas. So in last April, Gregor, Ben, and I initiated an anomaly detection data challenge, which we modeled after the previous LHC Olympics, which I think people here contributed a lot to, or
Years ago.
at least the development of the PGS was, yeah. So the before Delphis, in the dark ages, there was, before many of you were born, there was,
Last one was 08.
yeah, yeah.
That's the one I remember.
There was something called the Pretty Good Simulator that was developed by people here, I think, or Pearson here, which was used for detector simulation and produced LHCO files, which basically reduced features like the reconstructed objects in every event. Okay, so inspired by that, we wanted to revive that whole thing, and so we called it the LHC Olympics 2020 with a similar spirit. We prepared 3 black boxes of simulated data. Each had 1 million events with the 4 vectors of every reconstructed particle in the event. So, and we didn't do particle ID or charge or anything, no tracking or anything. So basically all these reconstructed particles are hadrons. And we subjected the events to a single R=1 jet trigger, PT greater than 1.2 TeV. And that was meant to give you 1 million events with leading order QCD cross sections that I already forget, but something like 100 inverse femtobarns, or maybe it was like 300 inverse femtobarns. Anyway, so that was constructed to be representative of the data, say QCD data, roughly now. Okay, and so the black boxes were meant to be representative of actual data, meaning they're mostly background and may contain signals of new physics. So here's where the emphasis differed from the first LHC Olympics that were held in 2005, 6, 7, and 8, I think. There, the expectation for the LHC was going to turn on was that, oh, the new physics is going to just like poke us in the eye, and it's going to be background free from the beginning, or the experimentalists, they'll handle the backgrounds. That's the easy part, right? And then the theorist's job will be to, after all the background's been cleaned away and there's like 1 million signal events left, we're going to figure out what the underlying Lagrangian was. So in the original LHC Olympics that some of you may have participated in, probably not, it was all signal. Okay, basically, right? So now we're in a different era, and so we produce these black boxes that are almost all background. Okay? And the goal is not so much to measure the signal Lagrangian, but to find the damn signal in the first place, or even to establish that it's there. Okay, so okay, all right. So that's the LHC Olympics, black boxes.
So when you say there's no particle ID, it means that it just a bunch of pions, and they're not. You don't know if they're even positive or negative charge.
Nope. Yeah. So a bunch of neutral hadrons, let's say, or I mean, we throw away all that information to keep it simple.
So it's just not available.
Yeah. So you're just supposed to focus on, I guess, like substructure and just to restrict the scope.
Just momentum.
Just for momentum. Yeah. You can imagine future versions of this challenge where we put in more information. Yeah. Okay. We also supplied a background data set of just 1 million QCD digit events. We told people how it was produced, and for anybody foolish enough to train data against Monte Carlo, we wanted to show people what would happen. Okay.
Is there a simulated magnetic field?
The detector simulation is Delphis.
But is it represent CMS or Atlas or both or neither? Just because they're different.
I forget. For this one, we used the CMS card. Yeah. So we had people submit to a Google form, just like in Nevada, what they thought the new physics was, how many events they thought there were before any cuts. People submitted Jupyter notebooks with plots, so it was good. People really gave it a good shot. We also asked for them to submit a p-value associated with the null hypothesis, which proved to be completely useless because we also weren't sure what the optimal. So we didn't have like the best p-value in mind. So people's p-values were all over the place, and we don't really know how they calculated them. So p-values are maybe not so useful. Okay, so 10 groups from around the world submitted results on box 1. 4 of them also submitted results on boxes 2 and 3. A number of additional groups couldn't finish the challenge in time because everybody waits the last minute and people complained. It was around Christmas time, et cetera, et cetera. So a number of people didn't get results on the boxes but did have results on R&D data set. And 7 of the groups were brave enough to give talks about their methods before we told them what the answer was. They were brave enough to give talks on what they found at the ML for Jets conference that just happened in New York. So people tried both supervised and unsupervised methods, and they tried a variety of different methods, including autoencoders, koalas, density estimation along the lines of what I described. And one group, the MIT group, even tried a biological neural network, which was Patrick Kaminsky looking at like 1,000 histograms, he said. And yeah, so
that's that biology.
yeah. So okay. So scanning histograms, not at all blind, right? Anyway, so this was what we did for box 1. So we revealed box 1 because there weren't enough submissions for box 2 and 3. We decided to postpone that, give people more time. But we did reveal the results for box 1. And so for box 1, we had 834 signals out of 1 million backgrounds. And we chose the same topology as the R&D data set. So for some people, this was a curveball. Some people really overthought it. Right? So in the end, we chose something which was basically the same as the R&D data set, with somewhat different masses. Okay. And this is what people found. So here's the so this is the MJJ, the invariant mass of this is the invariant mass of the 2 fat jets. And this is what people found. And you can see 2 groups got that thing pretty right. This group got it right by accident. It was a supervised classifier, I think. So they trained something supervised. And because the R&D data set had a pretty similar mass to the black box, they found basically
That was just
the right answer.
That was just luck.
Yeah. There was luck involved in this one too because they used the same 4 features that would work for the R&D data set, and yeah, so there's luck involved in this one as well. But these 2 groups nailed the invariant mass. This group also nailed the number of signal events and the mass of the first order resonance. So from that, we thought there was a clear winner, and the people who won were people from the Berkeley Center for Cosmological Physics. Okay? So a group from outside of our field participated and did the best on the challenge. And they used something
No wonder we
like...
haven't found anything.
Indeed. That is a lesson you could take from this. We need to up our game.
Now we're going to start doing cosmology.
Yeah, they have nothing more interesting to do, so everybody else in our field is too busy, right? Yeah, but they did discuss with Ben and I some of the things about the density estimation method, including the use of these 4 features. So there was some luck involved, but yeah, they did it all independently, and I think it's both a nice demonstration for this anomaly detection method using density estimation, and also a kick in our pants that some cosmologists came in and did better than us. Okay. In second place was a method by the Johns Hopkins experimental group. I forget if they're Atlas or CMS. But they used a combination of autoencoders and koala hunting, which they call tag and train, and which they're going to publish, I think. So that's nice. Okay, so stay tuned for more on the LHC Olympics. We'll be organizing a one-day mini workshop on anomaly detection in Hamburg the Saturday before the Boost conference, so on July 18th. There we'll reveal the answers for boxes 2 and 3 and discuss plans for a paper that we could all write together on new methods for anomaly detection. So there's still time to participate in that. And so let me just conclude. Sorry for going over time. These are, I think, exciting times for anomaly detection in high energy physics. Despite what you may have heard, there's quite a lot of discovery potential left, and I think a lot of room for innovation. And I think, model independent searches have a bright, there's nowhere to go but up, really. So they have a bright future ahead of them at the LHC, and maybe this is how we'll actually discover the new physics. So I didn't have time to tell you about applying the anode method to beyond HEP, but something that we're thinking about is applying it to various astro data sets, including the Gaia data, to find localized features in these data sets. That could be things like stellar streams, for instance. So this density estimation and anomaly detection method, I think, could have many applications beyond our field. So yeah, so thanks.
Any questions?
How did the Astro's density estimation work?
Okay, so they had so they developed their own, so their main interest was in this density estimator they developed, and they just wanted to look for some application of it. So this turned out to be a very good fit. I don't know all the details of their method, but it's something called analogous to what's called a normalizing flow. So it attempts to map, so it's similar in spirit to what we use, but it doesn't use neural networks. And a normalizing flow is a general method for density estimation which tries to map your feature space to one in which the random variables are distributed according to a Gaussian distribution, or according to a simple known distribution. It doesn't have to be Gaussian. So that's the normalizing flow, and it tries to do this iteratively in successive transformations. And so they had something like a normalizing flow, but without using neural networks, which they developed, and which seemed to work pretty well. So yeah, so all the things I was telling you maybe don't even require deep learning, maybe could be done using more classical methods. So they're planning to publish their method, on their own. I don't know if they're going to also discuss the LHC Olympics or not. But their density estimation, that's a huge field, is density estimation. There's a huge interest in that, so I think they have an interesting result there.
Any other questions? So let's thank the speaker again.
Very much along the lines of working in my students.
Now people at the LHC, they are going to have a let's say may just not right
Not the other.
Oh yeah.
Now people talking about this within environment and using a lot of data. For that, it has been using, for example, this we have one, or let's say how the energy going to be. Background, how the energy sticks out with
So it's not really a localized bug, it's more of a behavior on the tail. Yeah. Well, so that's also something we're thinking about, is how can we go beyond bump hunting to things on tails. But there, the sideband method is not as hard, right? So you need a way of getting the background estimate on the tail. Unless the background is really small, the signal is huge. Yeah. So for that, it's interesting.
Very nice talk.
Oh, thanks.
Hey, David, Max. Sure.
Yes,
Nice to see
nice
you.
to see you. Yeah.
You haven't been here for several years, if I remember.
It's been, like 5 years, I guess.
How much work was it